Hey y'all, welcome back. This is the second lesson of Unit 1, and this focus, we talked about limits last time. This lesson is actually going to be pretty quick, I think, because we're going to just focus on a specific type of function and how to determine limits of those functions, dealing with radical functions and rational functions and things like that, and how those combine. So our goal is to figure out the limit of a radical function, or a function, I guess that's not written the greatest, a function that might have radical expressions in it by multiplying by the conjugate. So it's pretty straightforward. But first, before we do that, remember conjugates. What is a conjugate? Remember that a conjugate is, like if you have a binomial, the conjugate of that uses the same two terms, but you just change the sign or the operation in between them. So the conjugate of x plus 7 is x minus 7. And so the reason that's important, or the reason it was important in the past, is when you were multiplying conjugates, it actually got rid of the middle term. Well, here today is an application of why that's important. And so when you multiply x plus 7 and x minus 7, or if you multiply two conjugates, you end up with x squared minus 49, which is a difference of squares. So if you needed to multiply all that out, you would FOIL all that out, and you would notice the plus 7x and the minus 7x cancel each other out, and you're left with x squared minus 49. Now, how does that help us? Well, we'll find out in just a little while. But one nice place is dealing with expressions that have radicals in them. For example, when you have rad x minus 4. Well, if I say rad x minus 4, now, if I multiply by the conjugate of that is rad x plus 4. If I multiply by the conjugate, I'm actually changing the value of the answer. So there wouldn't really be a context to just multiply by the conjugate. It's when you have something else going on. But the purpose of this problem is just to say, hey, let's multiply by the conjugate and see what happens. Okay? So these are conjugates, multiply them out. Rad x times rad x is what? Well, it's x. How do you figure that? Well, it's rad x squared, and the radicals and the squared cancel out. So you just get x. And then multiplying all that, I'll do it, it's plus 4 rad x, and then minus 4 rad x, and then minus 16. Those will cancel out, and you're left with x minus 16. So what was the purpose in multiplying by the conjugate here? Well, it's a mathematical trick that will help us. I wouldn't say trick, a mathematical idea that helps us get rid of radicals. Okay? So that's the idea there. If you were to multiply rad x minus 4 by its conjugate, you get x minus 16. Now, you can't just randomly do that on any problem that you want. You have to make sure that what you're doing is mathematically sound. But let's go ahead and take a look at an example of maybe where this plays out. The limit as x approaches 5 of rad x plus 11 minus 4 over x minus 5. Okay. So here, remember, what's the first step in determining limits? The first step is to substitute. So if I plug in 5 there, I get rad 5 plus 11 minus 4 over 5 minus 5. Put in parentheses around those. But you can see here we got rad 16 minus 4 over 0. Rad 16 is 4. And so we end up with 0 over 0. What do we call that? We call that indeterminates. Indeterminates. Now, indeterminate. What do we do then? Well, if we have an indeterminate form, remember the next attempt, or the next thing that we try doing, is we try factoring. Well, I don't know how to factor a radical expression here. It's weird. There's nothing you can really factor. So factoring is kind of out. So what do? The next step we try and do is multiply by a conjugate. In this case, the conjugate of the numerator. Because in the previous example, we were talking about multiplying by conjugates with the radical, because what did it do? It canceled out the radical. So let's go ahead and see what happens there. Now, I'm not erasing this as in it's not important. I'm erasing this because I need board space. You should always check for substitution first, and you should always show your work for that first, okay? But let's go ahead and figure out multiplying by the conjugate. Well, what's the conjugate of rad x plus 11 minus 4? That would be rad x plus 11 plus 4. And then we don't want to change the meaning of this expression, so we can't just multiply it by that. We have to multiply it by rad x plus 11 plus 4 on the bottom too. Because what's that mean? That means we're multiplying this expression by we're just multiplying by 1. And so we're not changing it. Okay, and that's important. So now when we multiply all this out, rad x plus 11 times rad x plus 11 is x plus 11. And then this is a difference of squares, so it'll just be minus 16. Okay, I'm not going to do all the work on that. Now on the bottom, we could multiply these binomials out, but I'm not gonna, and you're going to see why in a second. I'm just going to rewrite it, x minus 5 times rad x plus 11 plus 4. So we're taking the limit as x approaches 5 of that guy. Okay, so the top simplified pretty nicely. The bottom, I don't want to multiply that out. That's going to get ugly. And here is why. It's kind of cool. It's really cool. X plus 11 minus 16 simplifies to x minus 5. What? And then on the bottom, you get x. You still have x minus 5 times rad x plus 11 plus 4. Well, why is that important? Because now you can see that the x minus 5 on the top and the bottom reduce with each other. And so you're left with the limit as x approaches 5 of 1 over rad x plus 11 plus 4. And then from here we try substituting. So we end up with 1 over radical 5 plus 11 plus 4, which is 1 over rad 16 plus 4, or 1 over 4 plus 4, or 1/8. And so that is our answer for this problem. And that's kind of cool. So that gives you another tool to figure out limits. If substitution produces indeterminate, or if factoring doesn't work, then you can always try conjugates of some sort and see where you end up there. Okay? So let's just make sure I'm right here. We do end up with 1/8, and we're good. Now, here's another example or another practice problem. Go ahead and pause the video and give this one a shot. And notice it says to show the results in all different fashions, numerically, graphically, and analytically. All right, so I'm going to go ahead and do this analytically first because that's what we are focusing on, I guess, in the last problem. So we might as well do it in this problem as well. Limit as t approaches 0 of radical t squared plus 9 and then minus 3 all over t squared. And so we're going to try substitution. We end up with radical 0 squared plus 9 minus 3 over 0 squared. That's going to be rad 9 minus 3. So rad 9 is 3 minus 3 is 0 over 0. That's indeterminate. So we're going to try multiplying by the conjugate of the numerator. Sometimes you multiply by the conjugate of the denominator, but in this case, no. What is the conjugate of the numerator? Well, it'll be radical t squared plus 9 plus 3 all over rad t squared plus 9 plus 3. And then when we multiply that all out, we're left with t squared plus 9 and then minus 9. And then on the bottom, you're left with, again, you don't want to multiply those out, just leave them. Radical t squared plus 9 plus 3. And we're looking for the limit as t approaches 0. The 9 minus 9 cancels out, so we're left with t squared over, a lot of repeating what we're writing here, t squared plus 9 plus 3. The limit as t approaches 0. Those are going to reduce. So you're left with the limit as t approaches 0 of 1 over radical t squared plus 9 plus 3. And then we can substitute from here. We get 1 over radical 0 squared plus 9 plus 3. That's 1 over, that's all going to be radical 9, which is 3. So 1 over 3 plus 3, or 1 over 6. So this is the analytical approach, okay? And really, that's the proof approach. That's showing why it is what it is in a numeric sense, okay, or an analytical sense. Now, it did ask us to show the result numerically and graphically as well. Numerically means create tables. So let's go ahead and do the numeric approach. The numeric approach, we're going to create tables. Now, I'm not going to write that all out. I think I have the numeric approach here, so we're just going to work with that. Numerically means to create tables. So if I'm doing a left-hand approach, what are some t-values that I would try? Well, I might try, from the left, I might try -1, then -0.5, then -0.1, -0.01, and so on. We're going to type these values into our function, or type the function into the y list and type these values into our table. Right hand, we're maybe starting at +1 and going to 0.5, 0.1, 0.01, and so on. And we just plug those values into our calculator, and these are the values that we get. You can see those off to the side here. And what do we see? We see that it looks like, and if you actually scroll over those numbers, these ones specifically in the table, it's going to give you more accurate results. But it looks like it's approaching 0.166 repeating is what it looks like. Well, if you compare these results, if you type in 1.6 into your calculator, you would see that that actually is 0.16 repeating. So that's a numeric approach, what's on the screen there. The graphical approach means graph the function, see what it looks like. Now granted, you may not know what that looks like, so what I'm going to do is I'm going to type it into my calculator, into my y list. You should already have it there for the tables. I'm going to type in, let's see, radical, and I'm going to use x squared plus 9. It doesn't like when you use t's and things like that. Just use x anytime you have an independent variable there. And make sure you have parentheses around things so that it makes sense. And when you hit enter, make sure it's going to bring something up that matches that. And mine is saying syntax error, so I got to figure out where my error is. Still got a problem. There we go. So rad x squared plus 9 minus 3 over x squared. Now I'm going to go to my graph. Chances are your window is a normal window, like -10 to 10 and -10 to 10. And so you don't see much in your graph. You see, really, all you see is something that looks like this, just a line like that. But so we can see that the function doesn't really go very high at all. And if you look at your numeric approach and your analytical approach, you can see when t equals 0, it's only going to that height. So I'm going to go in and I'm going to change my window so that the y minimum says -1 and the y maximum says +1. So what that does is, instead of this being -10, or sorry, 10 and -10, we're stretching everything out, so this says 1 and -1, okay? And then when we go ahead and graph that, you're going to see a little bit more dramatic going on here, okay? And so you see something that kind of does this. It just goes up a little bit and then back down. Now, if you hit F3 to trace, your cursor is going to pop up and you can arrow through, and you can go from the left and you can kind of move your cursor over as x is approaching 0 from the left. You can see that the y value, it goes 1.622, 1.63, 1.64, 1.65, 1.655, 1.660, 1.663. So you can see it's approaching this. And then if you do the same thing from the right, you'll see that it's actually approaching that. Now in the video, or in the lesson off to the side, you're going to see this is a really dramatic graph. I really stretched it out. So instead of 1 and -1 is my bounds, maybe for my window I changed that to like negative, I don't know, 0.2 to 0.2. And so if you graph that, you're going to see more of kind of a spike there than you would have. But you'll notice if you were to hover over t equals 0, that it would say it's undefined, it doesn't exist, because when we substituted in earlier, we got indeterminate. All right, and then the analytical approach is, of course, the conjugate, which we just did, and we get 1/6. The point that I'm trying to make is that even though the analytical approach is the pure mathematical sense to proving things, you still need to understand things through tabular senses and through graphical senses. So understanding what a limit, the answer to a limit is graphically, is vitally important, and how to interpret tables is so important as well. All right, this is our last problem for this lesson. Like I said, this lesson is going to go by pretty quickly, and that's a result of our previous lesson taking so long. our exit problem says, what is the limit? I'm going to rewrite this. The limit as x approaches 4 of x squared plus 3x minus 28 all over x squared minus 3x minus 4. So go ahead and pause the video and see what you come up with, and then come back and see how you did. All right, for this problem, remember our first step is always substitution. We always substitute first, not because we're just trying to show more work than we really need to. Please do not have that in your mind. There is a reason in the future where substitution becomes absolutely essential, and if you don't do it, you will get the wrong answer, okay? If you don't do substitution and jump to the next step, that next step will produce the wrong answer. So please trust me that substitution is important. All right, 16 plus 12 minus 28 on top, 16 minus 12 minus 4 on the bottom. That's 28 minus 28 is 0 over 0. We call that indeterminate. Indeterminate. Now, what are our methods? Our methods are substitution. That didn't work for us. So we try factoring or multiplying by conjugates. You would think multiplying by conjugates would be the case here because that was the lesson, but don't overthink it. Don't try and read into the mind of the genius. What's the best method? We should recognize that this is factorable. So we're going to go ahead and try factoring. Now notice we have two quadratics, one on the top, one on the bottom. So the top factor is 2. That's going to be 7 and 4 plus 7 minus 4. And then the bottom factor is 2. 4 and 1. That'll be minus 4 and plus 1. So we can see when we factor it, we actually have things that reduce. Now, again, just to emphasize this is the same as this. These are exactly the same. They're just written in different forms. But when I start reducing, when I start dividing, I'm changing the function. And I'm changing it ever so slightly, but notice where I change the function. If I were to graph this and graph this, they would look exactly the same on my calculator. But in this problem, we had an issue at x equals positive 4 because of the x minus 4 factor here. So there is something going on at x minus 4 in this function. But when I reduced it here, there's no problem. There's no issue at x equals 4 here because you could plug it in and get a number. So these functions look exactly the same except when x equals 4. So just be cognizant of that these are not exactly the same, but they are the same everywhere except for at that little hole. So we're going to substitute now. So we get 4 plus 7 over 4 plus 1. That's going to be 11 over 5. That can simplify, but we're just going to leave it like that, 11/5 or 2.2. And that is correct. Okay, so that wraps up our lesson. Like I said, it was going to be short. Go ahead, and the homework on this is a PDF file. It's not found in your textbook. So go ahead and get that done. Make sure that you are getting a hold of me if you have any questions on anything so I can help you out. And I will talk to you later.